we will solve some problems related to power in AC circuits. Here is the first problem. We have to find the average power delivered to an impedance of 4 minus J3 ohm by a current given by this expression. So we have 4 ohm resistance in series with minus J3 ohm capacitive impedance, and the current through them is I, which is given by this expression. We have to find the power delivered to this impedance. Now, the RMS value of this current, I RMS, is equal to 5 by root 2. Therefore, power consumed by this resistance is equal to I RMS squared multiplied by the resistance, which is 50 watt. This is the power input to the resistance, and there will not be any power consumed or generated by the capacitor on an average. So average power input to the capacitor is 0. So therefore, this is the total power input to this impedance, 50 watt. Next, this is the second question. The voltage across and the current through a load are given by these two expressions. Suppose here is a load, then the voltage across it is Vt and the current is It. Since no diagram is given, let us by default assume that the current It is entering through the positive end of this voltage. We have to find the average power consumed by this load. So notice that the voltage is given as a sine function, whereas the current is given as a cosine function. Let us convert them both in a similar form. So we may write the voltage as 170 sine 377t minus pi by 6 radian, and here we have a minus sign. To make it plus, we may use a plus 180 degree. This is in volt, and pi by 6 is 30 degree. So let me put everything in degree for my ease. Then the current can be written as 8 cosine 377t plus pi by 6 is 30 degree. This is in ampere. Now we can change this cosine into sine by adding 90 degree here. Okay. Then this voltage is same as 170 sine 377t plus 150 degree, and the current is 8 sine 377t plus 120 degree. So the angle between the voltage and current is 30 degree. So power will be equal to VRMS, IRMS, cosine 30 degree, which is same as VRMS is 170 by root 2 volt, current is 8 by root 2 ampere, and cosine 30 is root 3 by 2. This is equal to 340 root 3 watt. This is the average power consumed by the load. Now move on to the next question. In this circuit, we have three voltage sources V1, V2 and V3. The expression of these three voltages are given. Notice that all the three voltages have same amplitude or RMS value, but the voltage V2 is leading V1 by pi by 18 radian, that is 10 degree. Okay, so if we draw a phasor diagram, then if V1 is here, the phasor voltage corresponding to V1, then V2 is leading this voltage by 10 degree. This is V2. Okay. They are very close to each other. The gap between them is 10 degree only, although I am drawing it quite larger. And then V3 is leading V1 by pi by 36, that means 5 degree. So V3 will be here. Now we also have R resistance, much smaller compared to omega L, impedance of these inductors. Then we have to find out which among these four possible statements is correct. Okay, so what is the relation among P1, P2 and P3, where P1, P2, P3 are the power output, average power output of these three sources respectively. Okay, so first let this current be I1, the phasor current. Okay, then the phasor voltage corresponding to this source is V1 plus minus V1 bar. Then the power output, average power output by the source P1 is equal to V1 magnitude of V1 magnitude of I1 and cosine of the angle between the phasors V1 and I1. Now, where is the phasor I1 in this diagram? I1 is equal to, so this current I1 is equal to V1 minus V2. If V2 is the phasor voltage for the second source, then V1 minus V2 divided by is R plus j omega L. Okay? R plus j omega L, but R is negligible compared to omega L, so we can ignore it. Okay. Then let us draw I1. Now V1 minus V2. So this vector is V1 minus V2 in this direction. So we have V1 minus V2 here. and then we have to divide it by j omega L to get the current I1. While dividing by j omega L, uh, this vector will turn 90° in the clockwise direction. So this will be the direction of I1 bar. This angle is 90°. Now we see that I1 bar uh, is in almost in the direction opposite to that of V1 bar. So this term cosine of angle between V1 and I1 bar, this term will be negative because this angle between V1 and I1 is close to 180°. So therefore P1 will be negative. So we have P1 less than 0. This is one observation. Now in the same way, let us see what can we say about P3. Suppose this voltage is V3 bar plus minus, and suppose this current is I3 bar, then I3 bar is V3 minus V2, V3 minus V2 divided by this R plus j omega L, R plus j omega L. Now V3 minus V2 will be somewhere here. So I can draw it here as well. It will be very close to this. This is V3 minus V2. And then when we divide this by j omega L, R is negligible. When we divide by j omega L, we will get I3, which will be here at an angle 90° from V3 minus V2 and lagging V3 minus V2. This is I3 bar. So once again, I3 is in a direction quite opposite to that of V3. So we can say that the angle between V3 and I3 is close to 180°. So cosine of this angle will be negative, and if we multiply this with the magnitudes of V3 and I3, we get the average power output from the source 3. So this is P3. Since cosine of this angle is negative, P3 is also negative. So we have P1 negative, P3 negative. Now what about P2? Overall in this circuit, we must have an energy balanced. Total energy generated or consumed by all the elements must be equal to 0. Since power output from source 1 and source 2 both are negative, so source 1 and 2 both are consuming power, then these resistances, no matter however small they are also consuming some power. So everything in this circuit other than source 2, they all are consuming power. Somebody has to generate that power, and that must be generated by source 2 only. Okay, since all other powers are negative or all other powers are consumed by the respective elements, then power generated by source 2 must be positive. So P2 should be positive, whereas P1 and P3 are negative. So therefore option C is correct. So let us move to the next question. In this circuit, we have a voltmeter with a reading of 200 volt, and the total power dissipated in this circuit is 1000 kilowatt. From this, we have to find the value of XL. How can we solve this? So notice we have 10 ampere current here. So this current is also 10 ampere. Here also 10 ampere. And the voltage from here to here, that is across the load, is 200 volt. So from this we can write that the magnitude of this load impedance, that is R square plus XL's square root of that, is equal to the voltage 200 volt divided by the current 10 ampere, which is equal to 20 ohm. Then the power consumed by this resistance is 2 ampere square into 1, so 4 watt power is consumed here, but the total power consumed is 1000 watt. So that means power consumed by this resistance is 1000 minus 4 watt, which is equal to 996 watt. And this 996 should be equal to this 10 ampere square, 10 ampere squared multiplied by R, this resistance. From this, we can get the value of R equal to 996 by 100, so 9.96 ohm. Now, if we put the value of R in this expression, we will get the magnitude of XL equal to 20 squared, 20 ohm squared minus R squared, which is 9.96 ohm squared, and then square root of that, this is in ohm, which is equal to 17.34. So XL will be equal to J 17.34 ohm, because this is an inductive impedance. So this is the answer. Now let's move to the next question. In this circuit, we have to find the value of resistance RL so that it can consume maximum amount of power. Notice that we have a circuit with two terminals between which RL can be connected. Therefore, according to maximum power transfer theorem, the value of RL, which will consume maximum amount of power, should be equal to the magnitude of the impedance of this circuit between these two terminals. Call them A and B. So for maximum power transfer to RL should be equal to the magnitude of the impedance of the circuit in box between A and B, between terminals A and B. Now we have to find the impedance of this circuit between terminal A and B, and that we have to find by replacing this source with its internal impedance, which is 0 for an ideal voltage source. Okay, so this internal impedance of this source is 0 ohm. Then if the impedance of the inductor is JXL, then XL is equal to omega into L. Omega is 1000. So 1000 into 4 milli ohm, and this is equal to 4 ohm. Then if the impedance of this capacitor is minus jxc, then xc is equal to 1 by omega 1000 into c. C is 0.5 milli, 0.5 milli, so 1000 above. This is in ohm. This is equal to 2 ohm. So this is equal to J4 ohm, and this is equal to minus J2 ohm. Now, inside the circuit, between A and B, we have two parallel paths, one with this 2 ohm resistance, and in parallel to that, we have this inductor and then this capacitor. The impedance of this path is J4 plus 0 minus J2 ohm. So J4 minus J2 ohm. So this is the impedance of this circuit between terminal A and B, and we have to find the magnitude of this. So this is equal to, let me write here, 2 and J2, they are in parallel. This is in ohm, which is equal to 2 into J2 divided by 2 plus J2. So the magnitude is 4 by 2 root 2 ohm, which is equal to root 2 ohm. And this is the answer or the required value of RL to get maximum power in RL. Now let's move to the next question. Here we have two circuits, circuit A and B, connected together, and there are two voltage sources and the sources are in same phase. We have to find the value of the resistance R so that maximum power is transferred from circuit A to circuit. To get the power being transferred from A to B, we need the value of this current here. Okay. Now, if we assume that this lower point is at zero potential reference, then this point is at 10 volt and this point or this point is at 3 volt. Then this current, if it is I ampere, then I is equal to 10 minus 3, that is 7 divided by R plus 2. If this R is in ohm, then R plus 2. Okay, so this is the current flowing here. And then if the voltage between this node and this node is V volt plus minus, then V is equal to 10 minus 2 ohm into this current, so 10 minus 2I. Then the power transferred from circuit A to B will be equal to the product of this voltage V and current I, V into I, that is in watt. Please note that the voltage and the current are alternating in nature, and therefore we should represent them as phasors. Although the phase angle can be considered to be 0 since they are in the same phase. Now the power is equal to V is 10 minus 2I, 10 minus 2, and I is 7 by R plus 2, 7 by R plus 2. This voltage multiplied by the current, which is 7 by R plus 2. This is in watt. This is equal to 10R plus 6 into 7 divided by R plus 2 whole squared. This is in watt. Call this power equal to P. Then to get the maximum value for this power, we can differentiate this expression of power and equate it to 0. So let us differentiate the power with respect to the variable R, okay, and set that to 0 to get the maximum value of power. So the derivative will be 7 into 10 into R plus 2 whole square minus 2R plus 2 into the numerator 10R plus 6, and this is whole divided by R plus 2 whole square. This implies that 10R plus 2, 10R plus 2 should be equal to 2 into 10R plus 6, which means 10R 20 minus 10R is equal to 20 minus 12, which is 8. That means R is equal to 0.8. So this resistance should be 0.8 ohm. Okay, and that is the answer. Now, to be more satisfied, you should find out the second derivative of this quantity and check whether that is negative or not to get maximum value. Okay, now let us move to the next question. In this circuit, we have a 220 volt voltage across this source, 122 volt voltage across this resistance, and 136 volt across this inductive load. From that, we have to find the power factor of this load. For this, we will use phasor diagram to solve this question. Okay. Suppose this current is I bar, the phasor current. Let me draw that here. This is I bar. Then the voltage across this resistance, call that VR bar, plus minus that will be in the same direction as the current I. So this is VR bar. Then suppose the voltage across this load is VL bar plus minus from here to here. And if the impedance of this load is Z angle theta, okay, then this voltage VL bar will be here at an angle of theta. So this is VL bar, and then this voltage from here to here, that is equal to the source voltage, will be the sum of VL and VR. Okay. So this will be the source voltage, Vs bar, phasor value of this source voltage. If we call it Vs bar from here to here, this side positive, this side negative. Then Vs bar is the resultant of VL bar and VR bar. So we can write from using trigonometry that Vs bar magnitude squared is equal to VR bar magnitude squared plus VL bar magnitude squared plus 2 VR magnitude VL magnitude into cosine of theta. Now the magnitude of Vs square is 220 squared, so we have 220 squared equal to magnitude of VR is 122 squared, magnitude of VL is 136 squared plus 2, here 122 into 136 cosine theta. From this we get cos theta equal to 220 square minus 122 square minus 136 square divided by 2 into 122 into 136, which is equal to 0.4526. And of course, this cos theta is the power factor for this load. Okay, so the answer for the first part is 0.4526. Then in the second part, the value of RL is given as 5 ohm, and we have to find the power consumed in the load. Okay, so load impedance we have assumed to be equal to Z angle theta, which can also be written as RL plus JX, RL plus JX, and this is also equal to Z cosine theta plus JZ sine theta. So from here we have Z equal to RL divided by cosine theta. RL is given to be 5 ohm. So this is 5 by 0.4526 ohm, which is equal to 11.05 ohm. Then the magnitude of this current I bar can be written as this voltage 136 volt divided by the magnitude of this impedance, that is Z. So that is equal to 12.31 ampere. So therefore we can write load power or power consumed by the load equal to 136 volt into 12.31 ampere into cosine theta power factor, which is 0.4526. This is equal to 758 watt approximately. That is the answer. Now, next question, which is here. In this circuit, we have to find the value of this capacitor C to get maximum power transferred to the load, this load. Now we want to solve this question without long computations. So therefore, please notice that load power implies the power dissipated by this resistance alone, because inductor and capacitor cannot consume any power. So the load power is same as the square of the current through this resistance multiplied by 1 ohm. So to get maximum power here, we would like to get maximum current through this resistance. Now let us consider this part of the circuit and convert it into its Norton equivalent. For that, first let us find out the impedance of this inductor. So that will be J omega L. Omega is 100, L is 5 milli. So that will be 0.5 ohm. And then the Norton equivalent of this green portion of the circuit will be a current source in parallel with this resistance and inductor in series, or inductor, this is 0.5 ohm, this is J 0.5 ohm. So this is the Norton equivalent, and between these two terminals we have this 1 ohm resistance and the capacitor in parallel. This is 1 ohm and this is C. Now consider this resistance and inductance in series. Suppose the impedance of this branch is Z bar, then 1 by Z bar, that is the admittance of this branch, is equal to 1 by 0.5 of 1 plus J ohm, which is equal to 2 by 1 plus J, and let me multiply the numerator and denominator with 1 minus J. So then this becomes 2 by 2 1, then 1 minus J. This is in Siemens. Now the conductance of this part is 1 and the susceptance is minus J. So therefore, this portion is equivalent to 1 Siemens conductance in parallel with an inductor with impedance of J ohm. So J ohm and 1 ohm in parallel is equivalent to this branch. Now let me keep the rest of the circuit as before. So you can check that these two circuits are equivalent. Next, let me put this resistance after the capacitor, and this is still equivalent to the original circuit. Now you see that this source current, Norton current, will have four possible paths. One through this resistance, another through this inductor, another through this capacitor, and the rest through this 1 ohm resistance. We want maximum current to flow through this 1 ohm resistance because we want to get maximum power in this 1 ohm resistance. Now, the phasor sum of these four components, these four currents, is same as this source current. Now, if we can adjust the value of this capacitor so that the current through the inductor and through the capacitor, they become equal and opposite to each other, then overall these two currents will add up to 0, and then the total source current will flow only through these two resistances. So we will get maximum current through this load resistance. So for that, we have to adjust the value of this capacitor so that the impedance of this capacitor is equal and opposite to the impedance of this inductor. So we need the impedance of this capacitor, which is minus J by omega C, plus the impedance of this inductor J. This should sum up to 0. That means omega C should be equal to 1, or C should be equal to 1 by omega. Omega is given to be 100 radian per second. So this will be equal to 0.01. So that means 10 milli infarad, 10 millifarad. And that is the answer.